Alright, so for this last part, in the second part of lab uh, B, we are going to talk about Bootstrap as an alternative to K for cross validation that we have seen in our previous video. Alright, to give you some idea about what a Bootstrap is, my understanding is that you might have some familiarity with Bootstrap, but let me start with a very basic example here. So for example, I have a data set from 1 to 5, so let me call it a fake data, and this fake data is then resampled using the sample function, and this resampled version, when we are doing it with replacement, is going to be 44141. So you can see I am repeatedly sampling from 4 and 1, but I'm completely ignoring 2, 3, 5. And what happens if I try to do it more often? Say for example, I try to do it 10 times. So this was done one time. So if I do it 1 time, 2 time, 3 time using a for loop, I'm doing it 10 times, right? So in each of these cases, say in here there is no 3, right? But in our original sample we had a 3. So say for example, in here I only have 4 and 5. I do not have 1, 2, 3 in here, whereas in our original sample I had 1, 2, 3. So based on the resampling, what can happen is that the same observation can enter multiple times, whereas some other observations, that for example 3, did not even enter even one time. But in another sample, 3 can enter multiple time, and there is no 1 or 2 in this particular sample, right? So this is with replacement. So why do we need such a thing, such as Bootstrap? Generally speaking, whenever we are working with a complex statistic for which we are not really sure what can be the appropriate distribution, what distribution that follows, and if that is the case, then we generally do not know how to make inference about it, how to calculate the confidence intervals. So to mitigate that, we resample such as this, and then we try to calculate the statistic from that resampled dataset, and we estimate that statistic, and then we try to get the standard error of that statistic from all of these resample. Just to give you a clear example, so the mean of the fake data 1, 2, 3, 4, 5 was 3, right? And then let me create a resampled version of that. That means if I do the bootstrapping 5 times, so I'm basically creating a list in here. In this list, I'm basically saving all of these bootstrap samples, right? And from all of these bootstrap sample, I try to calculate mean. So in, say for example, in this first sample, the mean would be 2.4. In the second sample, the mean would be 3.4. In the last sample, the mean would be 4.2. And then I can calculate the mean of this mean, which would be close to what we had originally, but the main interest is basically the standard deviation. And when we get this standard deviation, then calculating the confidence interval and things like that, that can be straightforward, because confidence interval is a function of standard deviation. So this was a relatively small example where I had b equal to 5. Let me take a even larger sample, and then you can see, you can get the standard deviation of means, you can get standard deviation of the medians. Not only that, you can also get not only a single number but also the distribution. See, the distribution of mean is looking like a symmetric distribution, right? But when you are taking the distribution of the median, you can see the symmetric type of pattern is there, but there are gaps in the data set. So that kind of shows you that the median's distribution is probably not as nice as your means distribution. And you can reuse this idea of calculating the standard deviation of a statistic for even complex statistics such as beta coefficient or the or it could be any other statistic, and empirically you can find the standard deviation from the distribution of the statistic from the bootstrap samples, right? So how is that relevant for our study? So for example, in our study, this is the first 6 observations, and you can see the IDs are like these, right? And then you can try to get a bootstrap sample where you can see the same ID can occur multiple times, right? Similar to the bootstrap idea. And you can see these samples are selected and these samples are not selected. And if you take the sample one more time, you can see a different number of samples are being selected in the sample, and there would be another sample that is not being selected in this particular bootstrap sample. But as you can imagine, similar to the cross validation, if you are trying to get the test data in this way and the training data in this way, say for example, these are the test data that are being selected and these are the training data, right? And say for example, in this particular example, this is the test data and this is the training data out of only these 6 observations. So you can imagine when we have how many 2600 observations in the entire data of this analytic 3 data set, you can similarly get a training data and the test data. This is basically known as the out of bag sample. So you can calculate your model in the training data, and you can use the test data to get the predictions and then use them to get the performance measures for those predictions, such as R-square, RMSE, and things like that. And doing this type of analysis by hand, you have to do a lot of coding. Fortunately, you have this caret package based on which you can simply use the train function, and in the train control you simply specify method equal to boot and the number equal to the desert number. Obviously in here I'm using a smaller number so that I can run this the R markdown very quickly, but generally 200 to 500 is recommended. And in this, what we can see is that you can run it 50 times. I'm only printing the head, that means only the first 6 rows, and I'm getting the RMSE and the R square for the first 6 rows only. But in total I should have 50. If you print out the entire fit for boot to $and resample, you should get entire 50 of these in each of these columns, and we can get a mean of the R square 22375. You see the mean of the R square is already printed when you print the fit for .boot2, which is basically the output of the train function. Also there is another method which uses a slightly different algorithm, which is known as the boot 632, and to use that, only thing you need to change is that in the train control you have to change method. Previously the method you were using is the boot, and now you are changing that to boot 632. Usually this kind of method is helpful to reduce bias, but in small sample this can give you some unstable results as well. So you need to be a bit worried about small samples. So in that case, when you are using this train function, you are still getting the RMSEs from the out of bag samples. Also that is the same that is happening for the R squares for the out of bag sample, and you can get the mean and standard deviations for those. right? So how do we really use this method? So we are basically using the linear model in a bootstrap sample that is not really changing too much. So let us work with a model that is basically changing. So depending on the sample size, samples, um, which training samples are selected, the model might change, and that will give us some idea about how stable or unstable our model is. So for example, when I'm calling a stable model, I mean that the model that did not have the multicollinearity problem, all of the VIFs were less than 4, right? So that was our formula 4 that I have showed in the previous video, and I have used that to calculate my R square. The R square was 0.229, and when I used a different formula where I included the collinear variable, remember the BMI variable, the weight variable, and these variables that were identified as a collinear variable, I still had those in my formula 3. I used that formula 3 using the step AIC. That means I'm doing a variable selection using the AIC method, and I am again getting 0.2287, which is very similar to 0.2293. So as I told you before, even though the VIF was more than 100 in some cases, that did not really change the stability of the model too much, even if we are using the AIC. Maybe if we use BIC, that could change. I don't know. We have to check that part. All right. So there is other algorithms for Bootstrap, and as you can see from this picture, there are some complex algorithm going on. And using that algorithm, I have written a function of my own. This is kind of like an optional component that I'm showing you here, where you can see the Optimism corrected version is showing you 0.2237, which is not very different than the other R squares we have seen, but the apparent one is 0.24. That means in the same sample where the model was fitted, you get the R square from that same sample, right? And we do this bootstrapping for how many times? I think 200 times. No, 50 times. And then after doing that, I get these type of estimates using an algorithm that translates this into R, right? Okay. So far we have talked about all of the techniques that were applicable to continuous variable. Now let us talk about binary variable, and instead of R square and RMSE, we need to work with some performance measure that can work with binary outcomes, right? So one of those performance measure is known as the area under the curve from the receiver operating characteristic, or ROC, and this is a measure of accuracy for classification models, because this binary variable as an outcome is a classification type of problem, and we need to use classification models such as logistic regression to fit that model. So in here we have to change some of the parameters. See, you have to say class probability equals true and summary function equal to true class summary, and then you have to specify GLM, binomial and ROC, and after you do that, you will get the resampled ROC values, and the mean is already provided, so you don't have to go through each of them. All right, so not only the bootstrap, but also the cross validation can be done for these logistic regression models, and you can estimate the ROC from the same process, right? Also, if you are particularly interested about some other measurements other than ROC, there is this Brier score, and there are other R packages like desk tool that has the function to calculate the Brier score from the model that you fit out of your GLM.